Dear students, now we'll discuss molecular orbital structure of Pyrrole. This is one of the very important question for 5 marks. Please note it. And you have the molecular orbital structure of Pyrrole, thiophene, furan, and also for the pyridine. One of which will definitely come in your exam for 5 marks or 4 marks. So that's why please have attention completely and please listen. So you already know, seen the structure of pyrrole, that is, this is the structure of pyrrole, a 5-membered heterocyclic ring. In the ring, if you see, there are carbon and nitrogen. So the carbon and nitrogen atoms are there in the ring, and both of them are sp2 hybridized. Both of them are sp2 hybridized in the pyrrole. So if you see, for carbon atom, the atomic number of carbon is 6, and if you see its electronic configuration in ground state is 1s2, 2s2, 2p2, and in the excited state, the electronic configuration of carbon in excited state, that is 1s2, this is 2s and 2p orbitals. So one of the 2s electron will shift to the higher energy orbital, that is 2p. So here it becomes 2s1 and 2p3. So if I put the box for these electrons, you know, inner orbitals do not involve in the hybridization. So that's why I am putting the orbital. This is 2s orbital, and these three are 2p orbitals. 2p orbitals. You know, in case of 2p, there is a px, py, and also 2pz. If you see here, in case of 2s, there is one electron. In 2p3, 1 electron. And for nitrogen, atomic number is 7. If you see the electronic configuration in ground state, that is 1s2, 2s2, 2p3. The same electronic configuration in excited state is 1s2, 2s, 2p. Here also in excited state, one of the s orbital, 2s orbital shift to the 2p orbital. So it is 2s1, 2p4. And if you put the box for 2s and 2p orbitals, so this is for 2s orbital, and I'm going to put the box for box orbital structure for 2p. Here we have 2p. So you already know this is one is the px, 2px, 2py, and 2pz. 2. Okay. So here in 2s there is one electron, in 2p 1, 1, 1. Actually, according to Hund's rule, we have to pair up this to first one orbital, but all of actually the degenerated orbital, they have same energy. But in excited state, the electron is always present in as highest energy carrying orbital. So here we have these structures. So here these orbitals, which one? These 2px and 2py, or any two of the 2p orbitals and 2s orbital involved in the hybridization. So these all three will involve in sp2 hybridization. So now then they will become sp2 hybrid orbitals. And here also the same thing happens. One of the 2s and 2p orbitals. So these two will become sp2 hybrid orbitals. And in case of carbon and also in nitrogen, there is one orbital which is not undergoing hybridization, that is 2pz here. So this is an unhybridized p orbital, and here it is also unhybridized p orbital. Okay, and in the case of carbon there is one unhybridized p orbital. In case of nitrogen there is also one unhybridized p orbital, it containing a single electron, an unpaired electron, with unpaired electron in case of carbon, and here in case of nitrogen it is containing pair of electrons, or electron pair of electrons. So unhybridized p orbital with pair of electrons. So we should have this summary with us. So for carbon we have how many? 3 sp2 hybrid orbitals, each containing unpaired electron. Those only will be involving in the sigma bond formation further, and one unhybridized p orbital. I hope you see till here, with unpaired electron, and for nitrogen atom there is also 3 sp2 hybrid orbitals and one unhybridized p orbital, here with pair of electrons. This is we got from their electronic status, and now we'll see the how they are forming bonds, and we can write the molecular orbital structures. This you may not need to write in the exam, because we should know how these all come. This is what you need to write. So from here, so now I will see the formation of first sigma bond. You all know in case of chemical bonding, so first formation of sigma bond takes place, then pi bond will continue. Formation of sigma bonds in pyrrole. Okay, there are 4 carbon atoms, one carbon, second carbon, another carbon, and one nitrogen. And you all know each of these carbon are have undergone hybridization, which is that is sp2 hybridization. So you must know when they undergo sp2 hybridization, their geometry will be trigonal planar. So please note down this geometry. So, and each carbon and each nitrogen have undergone sp2 hybridizations, hence they have occupied the trigonal planar geometry. So for example, I am not writing small lobe, I am writing only larger lobe. This all carbons and all nitrogen will have the same geometry in this case. So these 3 are the hybridized sp2 hybridized orbitals of carbon. For the same nitrogen also we have the same thing. So geometry you can see these all are having sp2 hybridization. So one of the sp2 hybrid orbital of carbon will overlap with the another sp2 hybrid orbital of carbon. So this, and each of them are containing unpaired electron. You can see the structure here. So here both of them will get paired up and forming a carbon-carbon sigma bond. So this overlapping is sp2 overlapping. This happens in all the cases. See here also this carbon, one of the sp2 hybrid orbital overlap with this carbon. So this is also sp2 overlapping. I'm just writing sp2. Here one orbital is there that is containing unpaired electron, and here also it is overlapping with nitrogen sp2, the sp2 hybrid orbital of nitrogen. So this is also sp2 overlapping, because nitrogen is also sp2 hybridized orbital containing sp2 hybridized orbital. You can see this is the overlapping, and in this case here also the carbon and nitrogen forming sigma bond by the overlapping, that is sp2 overlapping. Here also the same carbon sp2 overlapping, and each of the carbon and also nitrogen still containing an sp2 hybridized orbital with nitrogen, with unpaired electron. So you know the formula, molecular formula of nitrogen, that is molecular formula of nitrogen is C4H5En. We have just discussed about the carbon and nitrogen. There is also 5 hydrogen atoms. So these, the remaining sp2 hybrid orbitals of each carbon and this nitrogen will overlap with the s orbital of the hydrogen. So here this is the overlapping. This overlapping is sp2 of carbon and s of hydrogen. This is sp2 s overlapping, forming CH carbon, CH sigma bond. Here also the same thing. So you know the geometry of hydrogen orbital, that is only one orbital, 1s1. So the s orbital shape is spherical. So here also the nitrogen and hydrogen forming a bond, that is single sigma bond by the sp2 s overlapping. Here also the same carbon, remaining carbon also same thing happens. Here also the same thing happens. So what we get, this is the molecular orbital structure for the formation of sigma bond for Pyrrole. So we have to also write the inference of this sigma bond formation at the end. So here you can see there is 3 types of bond, that is one is CC bond, another one is CN bond, and another one is 4 types, NH bond and CH bonds. So these all are you have to write at the end. So first you should write at the end, that is carbon carbon sigma bond and carbon nitrogen sigma bonds. These both are formed by sp2 overlapping and carbon hydrogen sigma bond and nitrogen hydrogen sigma bond. These are formed by sp2s overlapping. As you all know, hybridized orbital form only the sigma bonds, otherwise they will just be as a lone pairs. So this is the molecular orbital structure for the formation of sigma bond to the Pyrrole. Now we'll, after the formation of sigma bond, we will now move to the formation of pi bonds. We will see now the formation of pi bonds. Yes, now we'll see the formation of pi bonds. Yes, we already got the molecular orbital structure of this for sigma bonds. That only I am writing, but I am forming its bonds here. This is equivalent structure to the carbon carbon sigma bond, carbon carbon sigma bond, the carbon nitrogen sigma bond, carbon carbon sigma bond, carbon nitrogen sigma bond, and each of them are having a sigma bond with hydrogens. So this is the equivalent structure. So that only I am writing here. This is the structure we get after forming the sigma bonds. And you know, each of the carbon and also the nitrogen still have a and one an unhybridized p orbital. So let me draw that. You know, the geometry of p orbital is dumbbell. So this unhybridized p orbital is present perpendicular to the plane of the sigma bond. So you know, if they are in the plane, then they form a axial overlapping, that is leading to the formation of sigma bond. But these all unhybridized p orbitals are present perpendicular to the plane of the sigma bonds. So that's why they always form the pi bonds. So in case of carbon, each of the carbon orbitals having a unpaired electron, and nitrogen is having a pair of electrons. These all will show the now sideways overlapping or lateral overlapping, upper lobe, lower lobe. Here also the upper lobe, lower lobe, upper lobe, lower lobe, upper lobe, lower lobe, upper lobe, lower lobe. So these will show the axial or sideways overlapping. This is actually the forming this structure. This is equivalent to the structure, that is carbon sigma bonds are already there. Yeah, hydrogen sigma bonds. And now they are forming a pi cloud actually. So this is like a cloud over the plane of the sigma bond and also the below the sigma bond, that is forming a sigma pi bonds. So now it is forming a cloud like this, pi cloud. Or there are totally 6 electrons are involving the pi cloud. Here 2 electrons, third, fourth, and fifth, and sixth here. So this is also this equivalent structure, or equally this is also equivalent to the structure of Pyrrole. If you do not mention the structure of nitrogen and carbon atoms and also hydrogen atoms, you can write like this also otherwise, or if you want to mention the pi bonds, when you mention the pi bonds, there are only 2 pi bonds and these lone pair also involving pi cloud. So that's why we can write like this. I have written. Okay. Yeah. This is the structure we get from this molecular orbital structure. That is the Pyrrole structure. So this is the molecular orbital structure for sigma bond formation, and this is for the pi bond formation. You can write both of them in the exam. That is very good. Okay. Yeah. This is about the molecular orbital structures of Pyrrole. Please note these: CC sigma bonds, CN sigma bonds, NH sigma bond, and CH sigma bonds are formed by sp2 overlapping and sps overlapping respectively, and these all the unhybridized p orbitals of carbon and nitrogen atoms will shows a sideways overlapping or lateral overlapping, that is forming a pi bond. So these both are the molecular orbital structures of Pyrrole. And we also have a very important small topic, that is the aromaticity of Pyrrole atom. So we all know that Pyrrole is an aromatic compound. So that's why we should give a proof, or we know the criteria of aromaticity. So whether it fits or fulfill all the criteria of aromaticity or not. If it definitely fills it, I know it is definitely fills and it is aromatic. So let us see that how it fulfill the criteria for aromaticity. So if you write the aromaticity, so you also, if you see the PYQs of your exams, most of the times for 2 marks also, that aromaticity of pyrrole, thiophene, or furan, or even pyridine also has been given. So you should know. So the aromaticity, you know, there are 4 criteria. The first criteria is the compound must be cyclic planar, cyclic and planar. You know, the pyrrole is having sp2 hybridization, so hence it has a structure of trigonal planar. So all sp2 hybridized orbitals are having actually gives a planar structures, hence it fulfills the first criteria. So you should here write completely like pyrrole is a cyclic planar structure. Okay, the second one, yeah, it undergoes conjugation. It shows the conjugation or resonance, conjugation and resonance due to delocalization of pi electrons. So in the structure you can see there are uh, 2 pi bonds, means 4 pi electrons and also lone pair of electrons. All these 6 are showing actually they delocalize and forming a resonance structures. We will see the resonance structures and reactivity in the next topic. So that's the third point is it should obey Huckel's 4n plus 2 pi electron rule. So you know it obeys the 4n plus 2 pi electron rule because here also n equals to number of ring is 1. So I'll write here n equals to 1. 4 into 1 plus 2. This is equals to 6 pi electrons. 6 pi electrons. In the structure, these 2 pi bonds gives 4 pi electrons, and this lone pair is also involving in delocalization, as just now I said. So that's why totally 6 pi electrons. Totally 6 pi electrons are there in the pyrrole. Hence it also fulfills the third criteria also. So all the first, second and third criteria has been fulfilled, and the fourth is that is the presence of at least one hydrogen, because we also know if it has to be an aromatic, it should show its properties like reactivity, that is electrophilic substitution. So it has how many hydrogens are there? So totally there are 5 hydrogens are there. In the formula itself we had 5 hydrogens. So there are, yeah, you can write like this. There are 5 hydrogen atoms present in the pyrrole compound. Hence they undergoes electrophilic substitution. So this also obeys or fulfills the fourth criteria. The fourth criteria, please remember, the compound must be cyclic and planar. The first criteria. Second criteria, it should show delocalization of pi electron, which is actually leading to the resonance in the structure, or it shows the conjugation. So that is also we can see in the case of pyrrole. We can see in the next class when we come to the reactivity. And it also obeys the Huckel's rule, Huckel's 4n plus 2 pi electron rule. You see it has a 4 pi electrons and the lone pair of electrons, all 6 electrons involved in the resonance structures, and they are actually responsible for the resonance. You know, the compounds containing 2, 6, 10, 14, 18 pi electrons are aromatic in nature. So it has a 6 pi electrons, so hence it is also aromatic in nature. In the fourth rule, it has a 5 hydrogens. At least we need 1 hydrogen for electrophilic substitution reaction, but it has 5 hydrogen atoms for the electrolytic substitution reaction, and it is also showing very easily the electrophilic substitution reaction because it has 5 hydrogen atoms. Hence all these 4 criteria has been fulfilled. Hence we can now declare that therefore the pyrrole is aromatic in nature. Pyrrole is aromatic. So this is very important. Sometimes they ask only the molecular orbital structure, and otherwise they will also ask write the molecular orbital structure of pyrrole and mention its aromaticity. Then you have to need to write all these things. Please note down. This is one of the very important topic in this heterocyclic compounds. And thanks for watching the video. Please like the video, share with your friends, please subscribe, and also hit the bell icon to get the updates of the next videos that will be uploading from me. Thank you. Bye me.